Okay, let me go through the theory part of today's topic, which is basically this is this is uh, 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 actually a ah, filter design too, but it's the IIR filter design more or less. Okay, starting from the facts about IIR filters. First fact is that these IIR filters are never linear phase filters. So if you really are have a criteria that all the frequencies should delay the same time on the system, then you cannot use IIR filter. You have to use FIR. However, saying that, there's also some say filters which has almost linear phase response, almost linear, not quite, but say quite nice approximation. However, the good part is that you will get much better amplitude response than, or actually more cost efficiently you get the better amplitude response than FIR filters. So basically you don't need to do that many calculations. So lower number of calculations than FIR. And that comes with the sacrifice, what you are sacrificing is the phase response. Applications, basically those are some of the applications which do not require the linear phase response, meaning audio filters, for example. You have quite a lot of, what is that called, wavelength dispersion already on air, meaning that the air carries frequencies at the different velocity. So it doesn't make any sense basically to try to do linear phase response since our media is not linear. Equalizers, well, that's also audio filter. So basically balancing the frequency components, so they looks, it sounds nice and looks good on your, the equipment. That's usually those lights. Yeah, feedback reduction. That's one thing actually. With the IIR, you have the feedback there, which can be used also to cancel the feedback. For example, mobile phones have these adaptive filters to match the echo, and it cancels out the echo part. Then we have, say, if we need high Q factor filters, then IIR basically is your selection. So high Q factor meaning that the Q factor is the width divided by the center frequency, or the other way around. The other way around, center frequency divided by the width. Narrower than the higher Q, yes. So basically, if you need very narrow filters, and again cost efficiently, then IIR is the only solution. The caveat on the IIR filter is that it has a little bit more complex design methods. On FIR, we have the windowing. You can still do it by hand. On IIR, well, it's back to the engineering tables and that kind of stuff, or tools. However, we have tools, free tools available on, for anyone to use on internet. It's full of them. Usually, some universities have put them there. But those are usually not optimized. And if you're working on a real workplace and need to design the filter yourself, then you ask your boss that you can buy some good program to do it. Okay, so complex design methods, but well, There's always a price to pay. At least those four. Oh, actually, the last one fits almost everything. The first one is bilinear transformation of classical, meaning analog filter. So where it starts from, it starts from the analog system transfer function. For example, a low-pass filter on analog domain, the transfer function would be something like that. Right, like Salenki low-pass filter looks like that, and you will set the resistors and capacitors such that you get, say, in S-plane, you would get Butterworth design. Right, remember that one. It's still, going. So that's the S-plane, complex S-plane, and those are the poles, and that's the cutoff frequency. I think that it goes something like that. Yes. All right. So if we have these parameters set for a certain cutoff frequency, then bilinear transformation is very simple. We will take the S and replace the S with 2 over Ts. Okay, 2 divided by Ts. So basically, this is Nyquist frequency. No, it's not. It's 4 times Nyquist. Okay, times Z minus 1 and Z plus 1. And after that one, you have H of Z. Simple. We have transfer function. You just make this one and you will get whatever terms you have. So the low pass filter actually will end up having, that will be denominator downstairs. So there will be C plus 1 squared, and then some other parameters, alpha Z squared plus beta Z plus gamma. Okay, so you will get a system in Z plane, and well, depending on whatever, you will get the poles inside of unit circle and double zero here. That's the bilinear transformation, how it treats a analog system transfer function and makes it a digital domain transfer function. Okay, a couple of things what happens here. So this bilinear transformation maps the frequency axis. So if we here have the continuous frequency scale, so from here to, well, infinity, frequency goes to infinity. On this discrete time system, sampled systems, we go only to the sampling rate over 2. And basically, the infinity maps at sampling rate over 2. So basically, it has some serious warping of the frequency axis. So it's not quite linear. It goes here, very small ticks of the original. But anyways, that's one method of making a discrete time filter, IIR filter, which has an analog counterpart. So this way we can design this whatever filter you can design with the Salenki analog filter structure. Yeah. Okay. And about the same restrictions, how many degrees you can actually put there on the analog filter before it says cuckoo. then you are basically hitting the limit of the accuracy of your resistors and capacitors, or actually accuracy of the capacitors. Then they start basically shifting the these zeros and poles out so that the it's not anymore what you think it is. Anyhow, well, this is one design method, bilinear transformation. So just replacement of the S with 2 over Ts z minus 1 divided by z plus 1. Easy to do even with the pen and paper, as long as you have the correct kind of filter designed analog way first. Then the next one is what I call parametric modeling. So what we basically do, we start from the differential equation of an analog system. Okay, not the transfer function, but the differential equation. And there we have these time derivatives. Well, you can actually draw a differential equation based on the transfer function if you want to. But anyways, this is more about the, say, physical system modeling. So you replace the time derivative with the closest approximation. Okay, so if you have dx over dt, you replace that with the difference between two subsequent points divided by time. So delta x over delta t. You replace that when you have a transfer function. Or you have the difference equation. You derive the difference equation from differential equation. Frequency space remains linear, but actually this works only for highly oversampled systems, since basically aliasing distorts the performance. So bilinear transformation doesn't have problems with the aliasing, since it takes the infinity frequency and puts that one to fs over 2. But this one actually, if there's some information that our sampling rate, okay, our sampling rate does not cover, then of course that information is aliased the spectrum. Okay, direct design. We will have some fun with the direct design today. So basically, this is when you automate this one, you get this optimized methods. So basically, it starts from the fact that we have a, I might actually have some pictures in here. Yeah, okay, that's one. Well, but anyways, we have the zero pole plot there. For example, we start from 1 point, set the degree number for the system, and then we can actually calculate the we can calculate the frequency response, and we can basically start tweaking these, for example, pole locations, or well, that's not right. In logarithmic scale, it goes like that. So we can start tweaking, for example, if we move these poles that way, we will actually tweak the this band, like that. Or if we move around, for example, that pole back and forth, we can actually adjust the gain on the lowest frequency components. Yes, we can do it. I don't recommend it, since this is eyeballing optimization, but we have also optimization routines that does it for you. You just set up the required system performance, and basically the tool will do all the fun stuff for you. But anyhow, so this will be kind of the idea behind of optimization. Or you can actually just use the transfer function coefficients. On the other hand, it'll in any case end up in the z-plane. And when you are on a z-plane, you can actually make sure that you do not accidentally move pole outside of the unit circle. If you are tweaking these system coefficients directly, then you have the danger that you will move those outside of unit circle, or lose some easily lose some the attenuation, because your zero position actually slips out of the unit circle. So okay, so this is the better place to start playing with on this filter design by direct design. But anyways, it's basically changing system coefficients or putting the zeros and poles to minimize the RMS difference, root mean square difference between the desired and your design. Okay. Then I have a nice curiosity called band stop notch filter. Band stop notch filter, what it is. Band stop notch filter is a simple second order filter which you can design by pen and paper. Practically the only one you can do it by pen and paper. And it has some use. Think of a typical measurement. Small signal, and you have amplifier there. You may have some open wires. What comes out usually is that you will have a signal looks like something like that. Right. And you should then basically just follow the mean of it. And actually you might actually have the 50 Hertz or 100 Hertz. 100 Hertz is usually more usual disturbance than 50 Hertz because of the regulation. The just AC to DC. AC to DC actually you will get 100 Hertz ripple. And well, those are also good sources of all kinds of noise. But anyways, which means that when you go into the signal spectrum, your data is somewhere in here, and then it has a huge peak at, say, well, let's put it 100 Hertz here. Nyquist frequency. How to get rid of that one? Since if you actually design a, one way would be to design an FIR filter which has a notch exactly at 100 Hertz. Another way of designing it is that we will design a filter IIR notch filter so that we have a notch exactly at that 100 hertz. And, okay, think of that one on the zero pole plot. Somewhere in here, you have the omega, which basically corresponds omega n equals 2 pi times 100 hertz divided by sampling rate. That will be the angle. Also complex conjugate pair here. And that's your notch angle. If you do the spectrum calculation out of that one, you will get performance like this one. It is already say it takes care of that notch, but on the other hand, it also starts distorting the data. What we can actually do, we can add a compensating pole on the same angle on certain distance. So this one actually would bring us some gain at the same angle. But of course, the gain can be almost infinite and still that one goes to zero. So what it does, that pole, it basically does something like this. So it makes the system almost unity gain anywhere else except on that notch angle or around the notch angle. Furthermore, remember the amplitude response. Has also a this graphical implementation or explanation. E to j omega distance to 0, e to j omega distance to pole. If we are very close to here, the distances to the second pole and pole and 0, they are equal. So the ratio also from here comes as 1 when we are in very close proximity of this point here. Okay. At the distance where omega, the difference in the angle is omega c, which is same distance as this range, omega c. That distance is roughly square root of 2 times omega c, meaning that on this distance, angular distance on both sides, we have minus 3 dB points. So we can actually design the whole thing by hand by setting up, okay, if this one, for example, is 10 hertz, then we just calculate what is the corresponding angle of 10 hertz, and we can put this pole at the correct distance from unit circle, and basically we have the full control of how this one looks like. So that's then okay. Let's make delta omega c. 2 times delta omega c is right here. Okay. We'll go through a design flow by with the MATLAB. when we have zeros and poles, then we can always calculate also the system coefficients. Okay, that's a so I have here the distance a from pole to unit circle, and the same distance as angular distance here. So this is roughly square root of 2 times the distance. Okay, good. So the next would be the classical filters. Classical filters meaning Butterworth, maximally flat passband, Chebyshev type 1 filter, equal ripple on passband, high attenuation on stopband, elliptic, equal ripple on passband, and equal ripple on stopband. These are the classical filters, which basically are analog filters, but using the bilinear transformation, we can do these a digital counterpart, and these are just fine filters. No problem with those. Okay. Earlier I told you about the phase response. The IIR filter destroys your phase. It's not totally true. If you are doing post-processing of the signal, you can always run the filter twice, one in positive time direction, another time negative time direction. You will get zero phase shift filter, meaning, okay, the signal does not direction. So yeah, so you get zero phase shift, but only for post-processing. This is non-causal filter. Another filter, this is not IIR, but that's why I changed the name of this section as filter design to it's median filter, widely used on digital filtering. It's say similar to running average, but instead of mean value, we are calculating the median of subsequent samples. This works pretty well if you have a signal which has occasional speckle. So if we have sometimes an error on data. For example, you have cheap sensor and you are reading it a little bit too fast, and then it gives you some funny results once in a while. How to get rid of those funny results? If you do linear filtering, then basically this was low pass filter, you will get bump on each of those. But if you do median filtering, you practically remove these from data. Okay, is that correct to remove real data? Yes, it is, if it works. Okay, and this median filter is widely used on image processing, since in images you have dead pixels or similar kinds of that. It has some, say, good properties. It works on some occasions. However, this is highly non-linear system, which means that it's totally non-deterministic system. It do not even have any. You cannot actually analyze that even with the, say, statistical data on exact kind of way. So mathematicians don't like this filter. It doesn't have any exact answer on the other sides. But engineering, well, if it fits the purpose, you will use it. Yep. So if you have data with singular peaks, then this as the first filter, pre-filtering for the say some linear filter would work just fine. And there's a image median filter, so low pass median filter. If you have single bad value or on image, you have dead pixel on your camera. So when you are calculating the median of those, it will be gray, and you replace that value you have basically that red value there, you replace by the median of its neighbors. It will be gray. So yeah, 3 by 3 median, and yeah, that's it. Okay, another kind of special kind of filter, matched filter. How to match the exactly the good morning outgoing signal shape with incoming signal shape. Matched filters are widely used, especially in radar technology. You do not have exact control of that radio wave pulse what you are sending, but you can measure it. So you basically just your model of sending a radar pulse might be that, okay, my radar pulse is exactly like this. But when you go into this highly nonlinear amplifiers on radio frequency, what comes out might be something totally different. Something like that. It does not matter if you measure that pulse form, then basically when you get a return from the enemy, already non-military things on these radars. Yes, a car. But they are also enemies, right? The car in front of you. Enemy. Okay. Do you have any car factories in this state? No, you don't. Hessen has Opel. Then, of course, Bavaria has BMW. And what is the Mercedes-Benz is from hell. Okay. But anyways, so Volkswagen, where's the Volkswagen made? In Germany, yes, but where in Germany? Okay. Oh, yeah, of course. Okay. Volkswagen. Enemy car in front of you. And your radar sends that pulse. And in order to measure the distance, it's time of flight correlation which is done. And basically there are all sorts of different signals around it, but on the receiver end, you can basically match this one when you have measured it, measured the data with that one. You will basically make a perfect filter. So that's actually digital domain filter. You make a perfect filter which is just a reversed data. And that works as a filter to your return. So that is called matched filter, since it only, actually it recognizes only this shape pulses that are returning back. Matched filter. Okay. Works also in acoustic radars. So the filter coefficients are generated simply by time reversing the known transmitter's pulse form. So you do not need to make the perfect transmitter, you just need to measure the transmitted pulse. Okay. So received reflected signal passes through the filter without attenuation. What is attenuation on the everything else? Well, heaven knows. Okay, that was the fun theory part of the other filters. So mainly IIR, and we start actually the MATLAB exercise by IIR notch. Then we move on and take a tool to make other the type of IIR filters. And you can actually see that this filter design tool actually works also pretty well for the FIR uh, filters too, as well as you can actually get the filter coefficients for external use. So this far we have been just playing with the MATLAB, but eventually during this course you will be implementing a digital filter uh, on that 32-bit ARM processor. And it's not that hard. I will give you some pointers how to do it, but anyhow, so I will make another recording of the MATLAB next.